Hi everyone, this is the lecture for Unit 7. Unit 7 is going to cover capnography, and just as a reminder, we will go back and cover Unit 6 later in the semester. Hopefully we will be back in classes for Unit 6. If not, we'll try to probably do that one more through a Zoom lecture, just so we can kind of go back and forth. I'm still working on getting a Zoom time of longer than 40 minutes as there's limited licenses for that, and it costs additional money for the anything over 40 minutes. So I will work on that. If you are listening to this lectures, again, this will be a lecture for Unit 7 over capnography. So capnography covers different terms, and you may hear all of these used interchangeably, but it will measure our end-tidal carbon dioxide, so end-tidal CO2. You may see it written as PET-CO2, which is partial pressure of end-tidal carbon dioxide. You may see it written PeCO2, which is partial pressure of expired carbon dioxide. And you may see it written as EtCO2, which just stands for end-tidal CO2. So all of those are talking about expired carbon dioxide, which is different than our arterial draw. So when we got our PACO2, which is partial pressure of arterial carbon dioxide, we had to do a blood draw. For capnography, we're just looking at exhaled carbon dioxide values. All right, so the term capnometry is the measurement of carbon dioxide in respiratory gases. And there is a difference between the two terms, capnometer and capnography, so you kind of have to keep those separate. A capnometer is the device that actually does the measuring of the carbon dioxide. And capnography is the graphic display of carbon dioxide levels as they change during breathing. So we'll talk the majority of the unit on a capnometer, which is the device that actually does the measuring. The end of the unit will go over different graphs that you would see displayed for different respiratory disorders, and that is capnography. Some indications to use end-tidal CO2 monitoring. It is primarily used in surgery during general anesthesia. That is a standard of care to have that available during any surgical procedure. You can use it during mechanical ventilation, and a lot of institutions are now starting to go to using end-tidal CO2 for everyone who's on mechanical ventilation. It just kind of depends on the facility that you work in. You can use it during intubation to determine tube placement, and the device that they generally will put on the end of an endotracheal tube after intubation is called an EZ-cap, and you see the picture on that slide shows somebody intubated with an EZ-cap in place. The EZ-cap will start purple when you take it out of the package, and then it will turn to a yellow color when carbon dioxide is introduced. So at 5%, which equals 37.5 torr, exhaled carbon dioxide, the EZ-cap will turn to a bright yellow. And to turn your percentage into torr, you would take your percentage times 7, which we'll talk about a little bit later in the unit. Excuse me, I misspoke. You would take your percentage times 7.5 or 7.5 to take your percentage and turn it into a torr value. You can use end-tidal CO2 to monitor respiratory failure. You can use it for COPD monitoring, and you can use it when you're weaning somebody off of mechanical ventilation. Carbon dioxide is produced normally in the body during metabolism, and it diffuses out of the cells and into capillary circulation, and then it returns to the lungs, and then we excrete the carbon dioxide with our exhaled gas. Instrumentation used, it uses the same principle as oximetry. It uses spectrophotometry, infrared light absorption. So PaCO2 is determined by the rate of metabolism and carbon dioxide production, the rate of perfusion of blood through the lungs, and the rate of ventilation of gas out of the lungs. And the instruments that you're used to monitor CO2 should be calibrated against room air prior to setup and then at each shift. And when you calibrate it to room air, remember there's 0.03% carbon dioxide in room air. So when you're calibrating that machine, it should calibrate to approximately 0%. There's two different types of capnometers. Use the right terminology. There's mainstream and side stream. Mainstream has the CO2 sensor located between the endotracheal tube and the breathing circuit. So you can see a diagram of the picture below there. You'll see the sensor is right in between the endotracheal tube of the patient and the breathing circuit. The other one is called a side stream, and that one has a sensor located on the main unit, and the CO2 is aspirated through a sample tubing connected to a T-piece adapter located between the endotracheal tube and the breathing circuit. So the side stream one actually has like a little, it looks like a little capillary tube. It's very small, and it actually goes from the patient's in between the patient's endotracheal tube and breathing circuit, and then that will go up into the machine that's doing the graphical or numerical display of the CO2. There's advantages and disadvantages of each type of capnometer. So we'll talk about the advantages first of the mainstream capnometer. This one has a sensor right at the patient's airway, so you get a very fast response in a nice crisp waveform. There's a very short lag time, so anything that you're seeing on the monitor is a real-time reading. And there's no sample flow to reduce the tidal volume. So as you'll see in a minute with our side stream capnometer, they do have to take a little bit of flow from the ventilator to draw up that little capillary tubing, or that little tubing that's going to the machine. Also, as we'll talk about here in a minute, our side stream capnometer doesn't show real-time readings. It has some lag time between it, whereas the mainstream capnometer, what you're seeing on the monitor, is what's happening at that moment with that patient. Some disadvantages of the mainstream capnometer. You can get secretions, and humidity can block the sensor or the window. So there is, if you go back to that picture that shows the mainstream capnometer, here I'll go back in on the lecture here, this little sensor on the inside of there, that can get secretions inside of there. It can get humidity inside of there, which will mess with the readings. The sensor does require heating to prevent condensation. It requires frequent calibration, and again, we're going to calibrate it to room air, which should calibrate to about 0%. It's a very bulky sensor at the patient airway, so let me go back to that picture again. You'll see this is a sensor that goes right onto the patient's airway, so it is kind of bulky and it is kind of heavy. So this is what it looks like here, a real picture of what it would look like going right over the between the endotracheal tube and the circuit. It's difficult to use with non-intubated patients, so we can use end-tidal CO2 monitoring with patients that are not intubated. Most of the time we have to do that through a side stream capnometer. The reusable adapters require cleaning and sterilization, so the adapters that you see going in between the breathing circuit and the endotracheal tube are not disposable. They are reusable, so they do require cleaning and sterilization in between the patients. So we'll talk about some advantages and disadvantages of the side stream capnometer. For the side stream capnometer, the advantages are you do not have a bulky sensor or heater at the patient's airway. They are disposable sample lines, so these sample lines that are coming up from the between the endotracheal tube and the circuit are disposable, so after the patient used it, it just gets thrown away. And you do have the ability to use with non-intubated patients. So if you see over here, this would be maybe a gentleman with COPD, and the side stream capnometer is just on the end of the simple mask there. Some disadvantages of side stream capnometer: secretions can block the sample tubing. So just like with the mainstream, you do have secretions that can interfere. There is a trap required to remove water from the sample. Frequent calibration is required, again, calibrating to room air at 0%. It does have a slow response to carbon dioxide changes, so because it has to draw some sample flow up and through that line, you're not getting real-time readings. You do have some lag time between carbon dioxide changes and the measurement that you see on the monitor. And then it does require some sample flow from the ventilator if the patient is being mechanically ventilated, and that may decrease their tidal volume a little bit. It's not a ton of sample flow that they're using, but it does take a little bit of flow from there. Capnography advantages. Just in general, it's useful in assessing trends in alveolar ventilation non-invasively. So we can get real-time readings, or maybe it's slightly lagged, but we are getting readings of carbon dioxide continuously without having to draw arterial blood gases to get that information. You can detect ventilation to perfusion imbalances caused by pulmonary disease or cardiovascular disease. You can very easily and quickly detect an esophageal intubation. If the patient is intubated in the esophagus, your end-tidal CO2 reading would be 0%. Or if you're using an easy cap, it would stay that purple color and not turn to yellow because you're not getting any carbon dioxide back from the patient if the tube is in the esophagus. It's good to use to assess blood flow during cardiac arrest to see if you're getting good blood flow to the patient, because if you're getting good blood flow, then you're getting carbon dioxide back as well. Determine appropriate PEEP levels. If the PEEP is causing air trapping, your carbon dioxide levels will start to increase. So if you're giving the patient too much PEEP, you'll see those CO2 levels start to increase, and that's very easy to see if you have a monitor attached to the patient at the time. It is needed to estimate physiological dead space, and remember the calculation for VDVT is PACO minus PICO over PACO. So you take your PaCO2, which you would get from a blood gas, subtract off your partial pressure of end-tidal carbon dioxide, which you could get off of the monitor, and then divide that again by your partial pressure of arterial carbon dioxide, which again you would get from a blood gas. This is a normal capnogram. So you'll see the graph displayed there to the right. And again, PETCO2, or partial pressure of end-tidal carbon dioxide, is usually given to you in a percentage. Normal is 4.5 to 5.5%. You would multiply that percentage by 7.5 to put it into torr. So an example, if a capnometer read 10%, you would take 10 times 7.5, and you would get an end-tidal CO2 of 75 torr, which we know is very high. Normal end-tidal CO2 is 33 to 43 torr. So that would be a high CO2, so they would be retaining carbon dioxide. Just know that it's used as a trending tool. This is not something that you hook up to a patient and get a carbon dioxide reading and then take it off. We're using it to see if the patient's carbon dioxide levels are increasing over time or decreasing over time, and that will let us know if there's any ventilator changes that we need to make or if there's something happening inside the patient that we need to be aware of. Again, it's not a one-time look at it tool. It is a trending tool. And like I said, normal partial pressure of end-tidal carbon dioxide is 33 to 43 torr. And if you look back in your notes and you remember partial pressure of arterial carbon dioxide is 35 to 45 torr, our end-tidal CO2 and our PaCO2 should correspond within 2 to 5 torr of each other. All right, so I'll stop this video and continue on with another one as we're getting close to my 15-minute time frame. So we'll stop here and I will continue with the next video.